So differential equations are a thing you're going to encounter in 17B. And yes, technically you have encountered them right now, but there's really only one differential equation that you all are talking about. And that differential equation is the following one. dy dt equals k times y. That is the differential equation that you're talking about. And we haven't really even talked about how we solve it, although you will talk about that next quarter. All we've really talked about is that the solution is y equal to c e to the k times t. And we can check that. So here, just to kind of see, if you take the derivative, dy dt is equal to, if we take the derivative of c times e to the stuff, it's going to be c times e to the stuff times the derivative of the stuff, and the derivative of k times t is just k. But look, that is literally just your function y multiplied by k. In other words, we exactly have that dy dt is equal to k times y. The reason I'm pointing this out so kind of explicitly, I really want you to kind of not be worried when you hear the words differential equation. For now, all that really means for any of us is that we're in this sort of exponential growth or exponential decay situation. Questions? What's that? K times y. That's a k. Yes, it is. Yeah, sorry. K times y. As expected. I guess there is one other slightly different differential equation. That's for if you have Newton's law of cooling. Although it's really the same. Newton's law of cooling just says the rate of change of your temperature is proportional to the difference between your temperature and the temperature of your surroundings. And then as we've seen as well, the solution just ends up being that the temperature minus the surrounding temperature is equal to c e to the kt. It's really the same equation. We're just kind of replacing y with t minus ts. So I'll say it again, differential equations, specifically when the rate of change is proportional to how much stuff you have, or the difference between how much stuff you have, you're always going to get this sort of exponential growth or exponential decay kind of thing. What that means for us is that when we're asked about this, we can kind of jump to the conclusion that, oh yeah, we know that this is our model for exponential growth or exponential decay when we have this sort of differential equation where the rate of change is proportional to the amount of stuff. So let's go and look at that question that someone was asking about. So one of the questions from, I think, Alameda's, one of his discussion worksheets was essentially something like the following. Told us that caffeine has a half-life of 5 hours. And then we're essentially told, although in many more, so part of the problem like this is distilling down what really matters. If you wouldn't mind, would you mind reading the question in full for us right now?
At a rate proportional to the current amount of caffeine in the body for all times. The half-life of industrial caffeine is 5 hours, and a monster energy drink contains 150 milligrams of caffeine. For simplicity, assume that a person ingests all 150 milligrams at the instant they drink a monster.
Great, thank you. So there were 3 things worth noting there, I think. One of them was that the half-life was 5 hours. The other one was that we ingested how many milligrams? 150 milligrams. And the third thing, which is kind of important, but not really that important, is that they said the magic words. Although really they didn't even need to say the magic words here, because once they said half-life, and when they say the words half-life, we know we're in an exponential decay situation. We know that the model is y equals c to the kt. But they also said the magic words before that, that the rate of decay, or what were the words exactly, is proportional to? Right, the rate, and so the rate of what? Oh, they just say that the rate is proportional. Okay, so the rate of change of the amount of caffeine, I'm guessing is the word that's there, is proportional to the amount, right? Those are the magic words. If the rate is proportional to the amount, that exactly means we have exactly this situation. Or then we're like, oh yeah, that's the situation, which means this is our model for growth or decay. Either way, right? Whether it's growth or decay, this is the model. So again, I'll say it again, don't get scared by the words differential equation. In this context, now I should say there are lots and lots and lots of other interesting differential equations that you will see some of. But for now, all it means is dy dt equals k times y, and we are in this sort of situation. So you're always going to get this when you hear the magic words. The rate of growth is proportional to the amount of the population size. Or I could alternatively say the relative growth rate is constant. Another way to say that. Cool. So we're told the caffeine has a half-life of 5 hours. We're also told that we're essentially starting with 150 milligrams of caffeine. So whenever I have an exponential growth or exponential decay problem like this, I typically like to write it down in the form of a table. I find that very helpful. And I should almost always have two data points, one time and one amount, and another time and another amount. One of the times I have is at the beginning of the process. So I want you all to write down what the time and the amount I have are at the beginning of the process. I'm thinking at the time of 0 time elapsed, I have 150 milligrams. You also know another time and another amount because we were told the half-life. So the half-life being 5 hours means that 5 hours later, how much stuff do we have? You could just say half, or you could say half, right? 75 milligrams. Okay. So then the first question, I believe, just asks us to, what are the words actually specifically for the first question, part A? Right. Right. So write down an equation for the amount of caffeine T hours after we ingest it, which really just means start with your model and find the constants C and K. That's what that means when they're asking you to write actual constants are, not just the generic ones. Almost always, if you're given time equals 0, the corresponding y value is your C value. I think you can skip the step of saying 150 equals C e to the k times 0, which then leads to just 150 equal to C. If you want to write that down, it's totally fine. And then we plug that into the model. So now our updated model is y equal to 150 e to the k times t. And then we're going to plug in our other data point to solve for k. So we're going to plug in 75 for y, 150 e to the k times 5 for t, and then we're going to solve for k. So we're going to get 75 divided by 150, so 1/2. It should always be a 1/2 at this juncture if you've been given the half-life. Equals e to the 5k, keep the natural log of both sides. Natural log of 1/2 equals just 5k, and the natural log of 1/2 divided by 5 is equal to k. So one way of writing the model here would be to write it as y as a function of t is equal to 150 e to the natural log of 1/2 divided by 5 times t. I don't remember which classes talked about doing this a different way, but another equally good way of writing this would be y equal to 150 times 1/2 to the t over 5. And the way I kind of justify knowing that one is that essentially I'm having the amount I have every 5 hours. this exactly accomplishes that. Because if t is 5, 5 over 5 is 1, 1/2 to the 1 is 1/2, and 150 times 1/2 is 75. No. Well, yes, but I'm not going to write that down. So I should say k is negative. Right? Natural log of 1/2 divided by 5 is a negative number. I don't need to add in a negative sign. You could, I find it annoying personally, but you could also write this if you prefer as y equal to 150. Watch what we get here. We get e to the negative natural log of 2 over 5 times t. That is an equivalent answer that actually has the negative sign in there if we want it in there. But again, I think the negative, go ahead, yeah, is completely unnecessary and kind of makes it harder to figure out what's going on here. Other questions about this? Cool. Yeah. I will point out again, like for example, if t was 10, here I get 150 times 1/2 to the second power. Here I get 150 times e to the 10 over 5 is 2 natural log of 1/2, but e to the 2 natural log of 1/2 is e to the natural log of 1/2 squared, which is just 1/2 squared. So it is really the same answer either way. And some people like this better. People like this better. Kind of depends. All right, and then there were a couple of questions we were asked after this. And I think I wrote them down somewhere, but I might have, oh, there we go, yeah. So yes, how long until there are only 10 milligrams of caffeine left? So part B, how long until the body only has 10 milligrams of caffeine? I always think it's a good idea to think about what your answer could be. So we know that every 5 hours, you're going to have half as much as before. After 5 hours, you have half of the, right? So I could get, yeah, like we can write stuff up here. After another 5 hours, we should have half of 75, which is 37.5, which is about 40. After another 5 hours, half of 40 is about 20. After another 5 hours, half of 20 is about 10. So I'm thinking it's probably less than 20 hours because I kind of rounded up there for a moment. You don't have to do that, but it's just kind of nice to know that your answer is going to look like what you're actually getting. All right, so the way to solve this is to set your value of the number of milligrams, which is y, equal to 10 equal to 10. So we're going to do 10 equal to 150 e to the natural log of 1/2 over 5 times t. Whenever you're solving an equation like this, or solving for time or for k, you always have to divide by this coefficient first. The first step is to divide both sides by 150. You get 10 over 150 equal to e to the natural log of 1/2 over 5 times t. Then we take the natural log of both sides, and we also simplify 10 over 150 as 1/15. So the natural log of 1/15 is equal to the natural log of e to the stuff is just the stuff. So natural log of 1/2 divided by 5 times t. Multiply both sides by 5. Divide both sides by natural log of 1/2. That is your answer. Sorry, off the page there. And then we can check and see approximately how much that is. 5 times the natural log of 1/5 divided by the natural log of 1/2. Going to be approximately 11.6. That seems, I made a mistake there. Well, so you guys can't see, can you see that? No, you can't. So I accidentally, what I typed in was natural log of 0.2 because I thought I saw a 1/5, not a 1/15. So I didn't do that on purpose, although it worked out perfectly. There's a really good example of why it was a good idea to do that work before, because I was like, oh, it should have been about 20 hours and I'm getting about 11. That seems really wrong to me. Oh yeah, it's because I made a mistake. I really would like to pretend like I did that on purpose, but I really didn't. But it worked out just wonderfully. Let's try that again. 5 natural. You guys really can't see that at all, can you? It's very dark. Okay, anyway. I'm doing it right this time. And getting natural log of 1/15 divided by the natural log of 1/2. And getting approximately 19.53. Excellent. Just as I imagined it would be. Hours. So that's how long it's going to take until, oh, question, yes. When you say you did the work first, what do you mean? So it is always my opinion that you should not do any approximating until the very end. So when I did this, I typed in the entire expression into my calculator. I didn't approximate like natural log of 1/2 as what, negative 0.7, I think, or 0.69 or whatever. So yes, I would say you might get marked off for that. It's always a better idea to approximate at the last moment possible. And the other question was, I thought this third question was actually kind of interesting. I don't think I've seen one of those before, where you also, who is drinking this many months? Don't drink. It's terrible. Sorry. One time my neighbor, who's a little guy way back years ago, was doing a science fair project and was having us taste test energy drinks for him for some reason. And then he's like measuring our heart rate. They were all terrible, but oh my God, no, 2 Monster Energy drinks, too much. Sorry, I'm ranting. Okay, let's get on with it here. So we drink one at what time? 1 p.m. And then we drink a second one at a very convenient number of hours later, 5 hours later, a full half-life. So, and then the question was how much caffeine is in the system at 11 p.m. Yeah. So what's our caffeine level looking like at 11 p.m.? So this is not a question we should try to plug numbers into a function for. This is definitely abuse and use the fact that we know exactly the half-life is 5 hours. So at time equal to 1 p.m., we know the amount of caffeine in our system is going to be 150 milligrams. And then 5 hours later at 6 p.m., well, 6 MP, no, 6 p.m., come on. We're going to have half as much as we had because of the half-life. We're going to have 75 milligrams, but then we're going to drink another one. So we're going to add on another 150 milligrams. So now we have, at 6 p.m., a total of 225 milligrams of caffeine in our body. And then 5 hours later, at 11 p.m., what a convenient amount of time, we're going to have half as much caffeine because the half-life is still 5 hours, regardless of if it's from the first one we drank or the second one we drank. So we're just looking at the total amount of caffeine in the body at this moment, and then from then on, you're going to have half as much 5 hours later. So 5 hours later, we're going to have a whopping 112.5 milligrams of caffeine in the body. Too much to go to sleep. Probably. I don't know. Maybe not. Maybe not for you all. Yeah. I think it's much more challenging to solve. So that's a good question. Let's actually see. And actually, I had an add-on question too. So yeah, let's see. So let me think about this 1 second. So I should say, if the first amount of time is a half-life, it's going to be easy regardless. So just for example, if it was this question and they said the first amount of time was still 5 hours, and then the second amount of time was say like, let's look at two situations. So same question, but now, so the first one we drink at 1 p.m. The second one is still at 6 p.m. But now we want to know what's our caffeine level looking like at, say, midnight. Because we really need to go to sleep. Well, this isn't too bad. Here's what we're going to do. I can't express enough how much I think drawing a table here is a good idea. You've seen me do it like every time. Hopefully that sticks and you all do it too, because I think it's a great way of kind of recording my data here. So at 1 p.m., which I might think of calling time equals 0, but I'm not going to worry about that right now. I have my 150 milligrams. And at 6 p.m., I have my 225, right? My 75 plus the new 150. So basically what I think I should do now, since I'm not going to be adding any more caffeine in, I should think of this as kind of my initial time equals 0. So I'm going to say, great, this is my time equals 0 at 6. What is wrong with me? I wrote MP twice. That's ridiculous. I'm losing it. Okay, so basically this is my time equals 0. And from there, I'm going to set up my y equals c to the kt. So I'm going to say, okay, y equals c e to the kt. And I'm going to have, basically the only thing that's going to change is my c value. So instead of having a c value of 150, now my c value is 225. But interestingly, it doesn't matter how much caffeine is in my system, the half-life hasn't changed, which means the K value isn't going to be any different than it was before. So you could do some work to find K here, but you shouldn't, because we've already done the work. Because if I plugged in, 5 hours later, I'm gonna have half as much stuff. I'm gonna end up getting right back to this equation here, where the 1/2 equals e to the 5k and the natural log of 1/2 equals 5k. So the half-life being constant means your K value should always be the same value. It's not going to change based on how much caffeine is in your system. So then we know that our model is y equals 225 e to the natural log of 1/2 over 5 times t. And then we can ask the question, what's your caffeine looking like at 12 a.m.? Meaning at time equal to how many hours later? 6 hours later. So then it would be y equals 225 e to the natural log of 1/2 over 5 times 6. And it'd be a little bit less than half of 225 because we've gone further. The question would be a little bit grosser if the first time interval was not 5 hours, because then the amounts are going to, so here's what's going to happen. We'll do that too. But just, so let's say we have the same question now, and I'm going to make it even worse. I'm going to say you drink one at 1 p.m., your caffeine is 150. You drink another one at 4 p.m. because you need the kick, I guess. And now the amount here is going to be challenging because it's going to be, well, we're going to use our model, right? So we know that after 3 hours, the amount's going to be 150 times e to the natural log of 1/2 over 5 times 3. Just using the model we already came up with, right? Back on the first page here. First page, second page here. Right? That's our model for the amount of caffeine, however many hours after drinking your first monster. Yeah. So there we go. And then I'm going to add another 150 milligrams to that. And then basically this is your new C value. So now our new equation, which is awful, is y equals to, let's just call this C. C e to the natural log of 1/2 over 5 times t. And then you can pick whatever other time you wanted to plug in to find how much you had however many hours later. So if we then ask like, what's your caffeine looking like at 7 p.m., then you would take this equation where again, this is the C value going right there and plug in time equal to 3. And I will point out, when I do this, I am reframing it to think of this as my time equal to 0 situation. Then this would be another 3 hours later. It wouldn't be a very nice question if they asked you not nice times, but it'd still be doable. Just yeah, good question. I like that. The other thing, the other thing I was going to ask was, and this is kind of a typical question I've seen in a lot of web work problems, is if we look back at part B here, which was, how long until 10 milligrams of caffeine remain, and we found that it was this time here. That's actually not the question I want to ask. I'm going to ask different questions here. So, looking back at our model for one more moment, promise we're almost done with it. We're only on part F now. So I want to know how much caffeine is in our system 2 hours after drinking the first and only. Well, that's probably the easiest type of question to answer because we already have found the model for the amount of caffeine in our body as a function of time. I'll remind you one more time, it's y equal to 150 e to the natural log of 1/2 over 5 times t. So So if that's our model for the amount of caffeine at time t, then we're just going to plug in time equal to 2 and get that y, or y of 2 if you like, is 150 e to the natural log of 1/2 over 5 times 2. That's not really the question I wanted to ask, though. The question I really wanted to ask is, what is the rate of change of the amount of caffeine in the body? There are two ways to do this, but I feel like there's one way that you're meant to do this kind of question. So here's what I'm going to do. I'm going to remind you all that the rate of change of caffeine in the body is proportional to the amount of caffeine in the body. Literally the words that were written in the problem. So to answer this question, we can literally take, sorry, I forgot one very important thing here. What is the rate of change in the amount of caffeine in the body at the same moment? At time equals 2 hours later. Sorry about that. Very important. So I'm going to use the K value we found, which was the natural log of 1/2 over 5, and then multiply it by the amount of caffeine that we just found, which is our 150 e to the natural log of 1/2 over 5 times 2. Or if you prefer, you could do it the longer way. You could say, hey, here's my function, y equals 150 e to the natural log of 1/2 over 5 times t. Take the derivative, because if you want to find a rate of change, you're finding the derivative of some function. So our derivative here, y prime, would be 150. The derivative of e to the stuff is e to the stuff times the derivative of the stuff, and the derivative of the natural log of 1/2 over 5 times t is just the constant, natural log of 1/2 over 5. And then you can see that if we plug in 2, we're exactly going to get the same thing we got right here. Our natural log of 1/2 over 5 times 150 times e to the natural log of 1/2 over 5 times 2. Same thing. So in my opinion, when they ask you this question about what is the rate of change at a particular moment, and they've already asked you how much stuff you have at the same moment, they really mean for you just to take the thing you found here and multiply it by your K. I will point out that even though you might not see it here, this answer is negative. Right, if you plug this into a calculator, it's going to come out as negative, specifically because right here, natural log of 1/2 is a negative number. All right, I think we've talked about the problem enough. Good problem, though. Thank you for asking it. I like that one. Okay, so again, differential equations just means we are thinking about exponential growth or decay. It means the rate of change is proportional to the population or amount of stuff you have. I will try, maybe that'll be the last time I say it today. All right, what else was on this long list of things that people had questions about? Oh yeah, related rates seem to be a very popular cause of concern. Related rates. Oh, there was something here. More shapes, yeah. Oh yes, a classic. So here, yes, here's a good, so we're brewing some coffee. On the subject of caffeine still, right? We'll keep it with caffeine. So we're brewing up some coffee and we have a, let's see, let me remember the phrasing here. Yes. So coffee drips from wow, from a conical filter, typical shape, right? With a radius, wow, the words just like my writing is feeling worse and worse every day. With a radius of r equal to 4 inches and a height of 8 inches. So coffee is dripping from this conical filter into a cylindrical pot, also with a radius of 4 inches and height of 8 inches. At a rate such that the volume. Sorry, it's been a minute since I've asked this question. How do we usually phrase this? Yeah, sure. The volume in sorry, brain, such that the volume is changing at 10 cubic inches per minute. How fast is the depth of the liquid in the filter changing when the liquid is 3 inches deep? A lot of words. Half the battle with related rates problems is reading those words and then interpreting and really kind of distilling what's important. Right, so let's see. We got coffee dripping from a filter with a radius of 4 inches and a height of 8 inches. So let's draw that. Let's just use a new piece of paper here because I know I'm going to have to write more than just this. So here's my conical filter, oriented in the typical way, right? If you've ever made coffee, or the filter points down like that. And it's got a radius of 4 inches. It's got a height of 8 inches. And it's dripping coffee into a cylindrical pot below it. So we've got coffee right dripping down into a cylinder with the same dimensions. It's got a radius of 4 inches, got a height of 8 inches. It's a very square looking pot. And we're told that the rate of change of the volume is 10 cubic inches per minute. So we know that, well, if we're talking about the the cone, then the rate of change of the volume is going to be, and I guess we have some volume in there, -10 cubic inches per minute. Right, because the volume in the cone is decreasing, right? We're losing liquid. It's going into the pot, right? It's transforming magically from water and beans into coffee. Chemically, not magically. And then we also want to know how fast that depth is changing, right? That's the question says, right? How fast is the depth of the liquid in the filter changing when the liquid is 3 inches deep? So we're asked to find what is the rate of change of the height of that liquid. I could be a little more specific here. We're asked to find this at the moment. I haven't done this before, but I think it's a good idea when h is equal to 3 inches. So we know that after we take the derivative of both sides of whatever equation we come up with, then we're going to plug in the values that we know. Specifically that h is 3 and dv dt is -10 and maybe some other stuff somewhere else, but probably not. Okay. So it seems like, as far as this question is concerned, the cylinder was completely extraneous, right? I didn't need to draw that at all. We will need to draw it though, because there's a second question here. So, okay. So then we're going to ask, or we're going to, find the equation relating the volume of the cone and the height of the cone, which I don't know if you're expected to memorize or not. The volume of a cone is always 1/3 pi r squared times h. And I'm specifically thinking about the cone of water here, or liquid. It's not water, right? You mixed it with bean juice, liquid. And the problem here, which you've encountered before, is that I have a variable I don't want, right? That r there is problematic. So what we have to do is we have to look at our cone and say, okay, well, great. The radius is 4 inches, the height is 8 inches. So we know that the radius is half the height. There are other ways to do this, but if you can literally just look at the radius of the big cone and the height of the big cone and see the relationship or the proportion, that is also true for any other radius and height. You could also say the radius is to the radius as the height is to the height, and then solve for r. You get the same thing. R equals 4/8 times H, so R is 1/2 H. And then we're going to plug that in for R. For volume now is going to be 1/3 times pi times 1/2 H quantity squared times H. Let's multiply it out. 1/2 squared is 1/4 times H squared times H, and then 1/3 times 1/4 is 1/12. So the volume is going to be pi over 12 times H cubed. And now we're in a good place to actually take the derivative of both sides of this equation. So we're going to differentiate both sides and get dv dt on the left equal to the constant pi over 12 hangs out. The derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. Now that we have taken the derivative of both sides, we're allowed to plug in our values. Just like with implicit differentiation, if you're trying to find the slope of a tangent line, after you've taken the derivative of both sides, you can then immediately plug in the point you're trying to find the slope of the tangent line at. Same idea, right? After you take the derivative of both sides, you're then allowed to plug in whatever thing you've got if it's that kind of question. So we're going to plug in what we know. We know that dv dt is -10. I'm going to reduce pi over 12 times 3 to just pi over 4. We know that h is 3 times dh dt. So I've got, and I might take the moment to simplify this right-hand side first. I've got -10 equal to 9 times pi, so 9 pi over 4 times dh dt. So I'm going to solve for dh dt. I'm going to multiply both sides by 4 over 9 pi, and the pi should end up in the denominator. -10 times 4 over 9 pi equal to dh dt. Or in other words, dh dt is equal to -40 over 9 pi inches per minute. Just a little bit more than 1. So you could either say the rate of change is -40 over 9 pi inches per minute, or you could also use more words and write out that the height of the water is decreasing at 40 over 9 pi inches per minute. Questions, comments? I see a couple of concerned looking faces. Yes.
Like, why couldn't you do like 2H? Like,
Why not replace H with 2R? Because the question didn't give me anything about R, right? The question told me, specifically the question said that, or asked how H was changing and gave me an H value, right? So this question says, how fast is the depth of the liquid? That's our H. In how fast is the depth of the liquid in the filter changing when the liquid is 3 inches deep, which is also our H. So that's why, and it's pretty typical for these questions for it always to be in terms of the height and the volume, not in terms of the radius of the volume. Not that you couldn't have that, just it's less common. But if this question had said like, how fast is the area of the water at the top of the cone changing, then you would have had to do it in terms of R. Sorry, it's somewhere. Where'd it go? It's right over there. Okay, missing. You put it on the table when you're done. Don't mind. So yeah, that's why we did that, because that's what we needed to do. Other questions about this one before we do more on this one? There is a follow-up question. How fast is the depth of the coffee in the cylinder increasing when the coffee is 3 inches deep? Feels like a weird way to describe the amount of coffee you have, but okay. So a similar situation, but not quite the same. So here's what we have. We have the coffee in our cylinder, it's filling up, getting ready to drink it. And we still have the same situation, meaning that the volume of coffee is, in this case, increasing, right? Because we're putting coffee into this thing, not taking it out of, at the same rate, which was 10 cubic inches per minute, I believe. I think. Let me double check that number. Somewhere around here, yes. So we know that for this problem, the rate of change of the volume is going to be a positive 10 cubic inches per minute. And now we're going to be asked to see how fast the height is changing. We want to know. Seems like a weird question to ask. We're like, why do we care how the height is? Like, it seems like a strange question to ask, but okay, it's just your typical kind of question. So how fast is the height changing? Again, at the moment, when the height is 3 inches. Also, right, just to remember the dimensions here, the height of this thing is 8 inches. The radius of this thing is 4 inches. Sorry, it's 4 inches. So same idea. We're going to write our equation relating the variables of interest. And we're probably going to get an extra one. That's okay. So in this case, we're going to have the volume is equal to pi times the radius squared times the height. And this is where someone's trying to trick you. So in the previous problem, the radius depended on the height, right? The radius was half the height. In this problem, the radius is 4 inches all the time. No matter how high or low you are in the cylinder, the radius isn't changing. So what we should really write here is the volume is going to be pi times 4 squared times h, or just volume equals 16 times pi times h. Not terrible at all. And if we take the derivative of both sides, I'm going to get dv dt equal to 16 pi times dh dt. This is an example of a problem where some of the information you have doesn't actually matter. It doesn't matter that the height of the coffee is 3 inches or 30, well, 30 would be overflowing, 3 inches or 5 inches. No matter how high the coffee is, the rate of change is going to be the same because of the shape that we're pouring the coffee into. So here, we're going to find out that 10 equals 16 pi times dh dt, and then we're going to divide by 16 pi to get that dh dt is equal to 10 over 16 pi, which reduces to 5 over 8 pi inches per minute. Regardless of how high up or how far down the coffee level is. So usually with related rates problems, they give you a rate, they ask you to find a rate, and they also give you like a moment where things are happening. And most of the time, you have to use the rate that you have, as well as the moment of interest to kind of plug in for all the things you don't know, except for the one that you're trying to find. This is an example where so some of that's kind of not exactly true, where we don't have to plug in the fact that they told us that the coffee was 3 inches high. Okay. Now, one more related rates problem, and then I think we'll start looking at some of this. The only person to post a practice exam who was Alameda. We'll look at some of that. Yeah. Also, FYI, in case you didn't see the announcement, we will not be having office hours on Thursday after class or on Friday afternoon. Sorry, I've got things to do. And unfortunately, well, I guess it's not so bad. We're probably gonna have to cancel class next Tuesday as well, which at least it's after your exam. Because I have a doctor's appointment that's extremely hard to change, so we probably won't have class on Tuesday. But it's the week of Thanksgiving, so I don't feel super bad about canceling class the week of Thanksgiving. Yeah. All right. So another related rates problem. This is a very kind of typical problem as well. A person who is 6 feet tall, not 5'10", is walking away from a 20-foot tall lamp, street light, I don't know, whatever. The source of illumination. How fast is, there's always so this question gets phrased in two different ways. Some people like to ask, how fast is the length of the person's shadow increasing? Some people like to ask, how fast is the tip of the shadow moving? And those are two different questions. I'm going to ask the one I like to ask, which is how fast is the length of the shadow increasing, but we'll talk about the other one. So how fast is the length of the shadow increasing when the person is 25 feet away from the base of the lamp. Oh, street light. Good God. For most problems, I would typically draw a picture. So let's draw a picture. So here's our street light, source of illumination. And then here's the street that we're walking on. And here's the guy or the girl. Maybe drawing them a little too tall, if that's supposed to be 20 feet over there, whatever. And then their shadow is being cast like this, right? There's their shadow. And the person is walking that way. All right, so let's label what we know. So we know that the street lamp is 20 feet tall. It's not changing. And the person is 6 feet tall. That's also not changing. But two other things are changing, specifically how far they are from the street lamp and how long their shadow is. I would typically call the thing that I'm trying to find the rate of change of X, although it doesn't really matter what you call what, and call this other one Y. Although really any variable letters you like to use are perfectly acceptable, as long as you label things appropriately. You can call them A and B or Z and R or whatever. So we want to find dx dt, the length, the rate at which the length of the shadow is increasing. And we are told how fast. Oh, were we told how fast? I forgot a very important piece of it. Oh my gosh. Holy smokes. So looking at this problem, you might have noticed that nobody said anything about any rates. Yeah, I failed here. So note of importance, our person is walking at a rate of 4 feet per second. Sorry, that's important information. So now that we've said that, we can say that dy dt, how fast the distance between them and a stationary object, should be 4 feet per second. Sorry, how fast the distance between them and a stationary object is increasing should be 4 feet per second. And we want to know how fast the length of their shadow is increasing. And just like every other time we do a related rates problem, once we know the thing that's changing and the thing we want to know that's changing, we're trying to find an equation relating those two variables. Preferably only those two variables. But in the case of like a cone, sometimes you get more variables than you want. That's just how it's going to go. So here, we need an equation relating x and y. I see some similar triangles. So I'm going to see that there's a big triangle whose sides are 20 and x plus y, and a smaller triangle whose sides are x and 6. So really any ratio is fine. You could say base to height equals base to height, or big height to little height equals big base to little base, or really take your pick. I might choose to do it in a way so that all my x's and y's ended up in the numerator. So I might say, great, this base divided by that height, this larger base divided by this larger height is equal to this smaller base divided by this smaller height. I'll point out that really I'm just picking which trig function I want to use. Technically what I'm doing here is I'm saying that if you think about this angle being theta, that cotangent of theta is either x over 6 or cotangent of theta is x plus y over 20, and they should be the same. Also a fine way of doing it, but kind of weird. So then before we so most of the time at this point we differentiate both sides. Here I would recommend simplifying first. So I'm going to cross multiply and get 6 times x plus y equals 20 times x. Might as well keep going. 6x plus 6y equals 20x, and 6y equals 14x. And now if we differentiate both sides, we're going to get 6y equals 14x is going to become 6 times dy dt equals 14 times dx dt. I was told dy dt, it's right there, after we remembered that we needed to say it. So we have that 6 times 4 equals 14 times dx dt, or in other words, dx dt is going to equal 24 divided by 14 feet per second. Notice, once again, atypically, we didn't have to plug in how far away the person was from the lamp. Or in the previous problem, how high the water was or the coffee was when we were trying to find the rate of change of it. That's a kind of atypical, but sometimes happens. So it is true here. It doesn't matter, assuming like you project the light forever and there wasn't any curvature or whatever. If you kept walking away from this lamp forever and ever and ever, the rate of change of the increase in the length of your shadow would always be whatever this number is, 12 over 7 feet per second in perpetuity. Whether you're 25 feet away or 2,500 feet away, your shadow would still be increasing at the same rate. Now, the other question people like to ask here is, how fast is the tip of the shadow moving? And when you ask how fast something's moving, you have to say, okay, how fast is the distance between it and a stationary object increasing? In other words, what we're really asking here is, how fast is y plus x changing? The answer is really easy. It's how fast the person is walking plus how fast the length of the shadow is increasing. Right? Because the shadow's already increasing at whatever rate it's increasing at, and I'm just walking at whatever rate I'm walking at. So I'm just pushing it forward while it's still increasing at whatever rate it's increasing at. But we can do the math. The math is super straightforward. The question here is, what is the rate of change of x plus y? I'm sorry, you can't see that. In other words, find the derivative of x plus y. Well, this is one of those great instances where one of our derivative rules that we never actually really use, but we use all the time, we're actually going to use explicitly and say, oh yeah, remember how when you take the derivative of the sum of two things, it's equal to the derivative of the first thing plus the derivative of the second thing? This is exactly the time where it's good to know that, because then we say, oh, we already know both of these things. We just found that dx dt is equal to 12 over 7 feet per second. And we were told that dy dt is 4 feet per second. So we're literally just adding together how fast the length of the shadow is increasing plus how fast the person is walking. It's kind of cool. I mean, it seems sensible, right? You're asking how fast the tip of the shadow is moving. This is just how fast I'm walking plus how fast my shadow is increasing in length. And simplifying this, it's 12 over 7 plus 28 over 7, which is 40 over 7 feet per second. Cool. All right. Let's take a look at this practice exam 2 from Alameda. Lots of good questions on here. Not this first. Actually, I should point out this first page because I do think there's a couple things that are worth making sure that you read through. All this, yeah, whatever. But specifically the instructions. Unless the problem explicitly states otherwise, you absolutely must show work. A correct answer without a reasonable amount of work will be given a 0. You are allowed 1 page of notes. That's nice. Please use your note sheet to cover your exam solutions whenever possible. Okay, sure. You do not need to simplify your final answers. That's good to know as well, right? So don't spend time simplifying if this is your test instructions. Please do your final answers in the boxes at the bottom of each page. So definitely write. Now, I imagine the instructions for Varn and Lewis might not be exactly the same, but they're probably still worth making sure you read them when the exam starts, or if they're posted ahead of time before the exam starts. So I would, again, focus specifically on the fact that I'm allowed 1 page of notes, Is that true? And also, do not need to simplify your final answers. That seems like a big deal too. You shouldn't spend time simplifying your answers there. Okay, in fact, this is not the version I want here. Sorry. There we go. So here's the first question, which we're going to do, a couple of. Use the definition of the derivative to calculate the derivative of f of x equal to 1 over x squared. To be clear, he's even going to give it to you here. You must compute the limit as h approaches 0 of f of x plus h minus f of x all for h. And in my mind, there's probably like 3 different types of limit definition questions one might ask. This is one of them, where you have a fraction. So doing it this way, the limit as h approaches 0 of, okay, if this is f of x plus h, I'm just replacing the x with a parentheses. And then whatever is in the parentheses goes in the parentheses. So when I start off here, my fraction is going to be my f of x plus h, which is 1 over x plus h squared, minus my f of x, which is just 1 over x squared, all divided by h. Okay. When you're doing one of these limit definition of the derivative problems, your ultimate goal is always to cancel out that first h that's in the bottom. Nothing else though. Nothing else, but not that you shouldn't, but like I take that back immediately. The intermediate step is to cancel out the not h things in the numerator. For fractional ones like this, we have to get a common denominator. So we have to write this as the limit as h goes to 0 of, I'm going to take this 1 over x plus h squared and multiply it by x squared over x squared. And I'm going to take this 1 over x squared and multiply it by x plus h squared over x plus h squared. And for these problems, there is never like a simpler common denominator. It's always just the garbage in one denominator times the garbage in the other denominator. That's always how it's going to be. It never is nicer than that. We can make this a little bit less terrible, though, by doing the following. We're going to write this as the limit as h goes to 0. And then instead of dividing by h, or dividing by h over 1, in the next step, we're going to multiply by 1 over h so we don't have fractions and fractions anymore. So we're going to write this as x squared over x plus h squared times x squared minus x plus h squared over x squared times x plus h squared. All of that times the reciprocal of h over 1, which is 1 over h. It's just less terrible to write. Okay, here's what should happen, or here's what we should do. We're going to simplify the numerator because essentially we need to do stuff to the numerator until we can get all the not h things to cancel out, so then we can factor out an h and cancel out the h that we want to cancel out. But you shouldn't mess with the denominator at all. Leave the denominator as is. Don't multiply it out. It's not to benefit because essentially after we cancel out this h here, we're expecting all of the rest of the h's in the denominator just to become 0. So there's really no benefit to multiplying out the bottom. You're just wasting your time. On the other hand, we definitely do need to simplify the numerator here. So the limit as h goes to 0, I have, first of all, this is one fraction because I now have my common denominator of x squared times x plus h squared. And the numerator I have x squared minus all of x plus h squared, which I do need to actually FOIL out. X plus h times x plus h is x squared plus 2xh plus h squared. All times 1 over h. We then distribute the minus sign. You get the limit as h goes to 0 of x squared minus 2xh minus h squared all over x squared times x plus h squared times h. Yes, instead of saying times 1 over h, we just move that h over to the denominator there. Now, the x squared minus x squared is 0, and everything else in the numerator has an h in it. I like to take the additional step of factoring out an h and rewriting it as the limit as h goes to 0 of negative 2x minus h all times h over x squared times x plus h squared times h. And finally, I can do what I wanted to do and cancel out the original h that was in the denominator. Not any other h, specifically this first h here. That one is the one that is canceling out, not some other one. But now that means we're left with something where we can actually plug in zeros for the rest of the h's. Because now I won't end up dividing by 0 when I do that. I'm going to get negative 2x minus 0 over x squared times x plus 0 squared. And we simplify this, it's going to become negative 2 over x cubed, or negative 2 times x to the negative third. Either way is fine to write it. I'm just writing it this way to point out that you would have also gotten the same answer just using the power rule. Again, not that you should have used the power rule here because the instructions very clearly tell you what to do. But if you think of this as x to the negative 2, the derivative is definitely going to be negative 2 times x to the negative third. So it's nice to see that our answer actually is what we would expect it to be. Okay, there's two other types of questions I think you could get asked as far as limit definition, or that seem reasonable to ask, where the function's either got a square root or it's just a nice quadratic or cubic polynomial. Those are kind of typically the types of questions one would ask. Let's do one more. Let's say we want to do the same thing. Find the derivative of f of x equal to the square root of 3x plus 1. Using the limit definition. So it's really, really important that we correctly write f of x plus h, right? Because our limit definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. I think the easiest way I've ever kind of said it is just to rewrite this expression, this function, and just replace every x with an open parentheses. So f of parentheses is the square root of 3 times parentheses plus 1. And then into the parentheses, x plus h. And then we can write this out. Okay, this is going to be the limit as h goes to 0 of the square root of 3 times x plus h plus 1 minus the square root of 3x plus 1 all over h. Now what? We have to multiply by something. The conjugate. So we're going to rewrite this as the limit as h goes to 0 of the square root of. Now I would take a moment here. I know I said you don't want to multiply stuff out, but I find this I think it's easier to write this as 3x plus 3h instead of writing it as 3 times x plus h. Either way is fine. If it's an easy enough simplification where it doesn't really matter, I would prefer to write it the way that I feel like is easier to write it. So the square root of 3x plus 3h plus 1 minus the square root of 3x plus 1 all over h times the conjugate, which is just the same square root expression except with a different sign in the middle. It's going to be the square root of 3x plus 3h plus 1 plus the square root of 3x plus 1 over the same amount. Okay. The whole reason we multiply by the conjugate is because when you multiply this thing by its conjugate, you get the first thing squared minus the second thing squared. You don't need to multiply to see that the middle terms cancel. We know they cancel. So we're going to get here the limit as h goes to 0 of the square root of this squared is just going to be 3x plus 3h plus 1. And minus times the plus is minus. The square root of 3x plus 1 squared is 3x plus 1. Be careful here. When it's a minus the whole thing, you can't just write minus 3x plus 1. We have to write parentheses around that to make sure that everything gets a negative assigned to it. The denominator, we're just going to leave as is. It's going to be h times all this stuff. Square root of 3x plus 3h plus 1 plus the square root of 3x plus 1. We simplify the top. And I'm going to point out that the 3x minus the 3x will cancel, and the 1 minus the 1 will cancel. So we're going to be left with the limit as h goes to 0 of just 3h on top divided by h times all that stuff on the bottom. Here we don't even have to factor out an h because there's only one term, so the h's just get to cancel. So 3h divided by h is just going to be 3 on top. And now I think, so I don't really write this next up, but I think you can skip it. So now that we cancel those, we can just plug in zeros for the rest of the h's and get 3 divided by the square root of 3x plus 0 plus 1 plus the square root of 3x plus 1. Those are the same, and although technically, since the instructions said not to simplify, you could leave it alone. Technically, we're done. But I would want to simplify this one. So the square root of 3x plus 1 plus the square root of 3x plus 1 is 2 times the square root of 3x plus 1. But I would point out that if you submitted this answer and he said, no, you didn't simplify enough, like, you said you didn't have to simplify. This is full credit. I did the right thing. It's the right answer. So don't get marked off for not simplifying if you don't like if you get marked off for not simplifying and you weren't supposed to simplify, say words. Like, don't let that go. Okay. Continuing on. What else do we have here? That's a good one. Find the equation for the tangent line to the graph of y equal to 2x plus 1 over x squared plus 1. I'm almost tempted to make it an implicit differentiation problem. Technically, I could multiply both sides by x squared plus 1 and then just do it implicitly. Should I do that? Probably not. Probably definitely not what he's expecting you to do. So I would mention it is a good idea to do the problem in the way you think your teacher is expecting you to do it, if you can, right? Like, if you see some wacky way of doing something, you're like, well, that's probably not what they meant for me to do. So let's do this the typical way and find y prime using the quotient rule. So it's going to be the bottom times the derivative of the top, which is 2, minus the top, in parentheses, times the derivative of the bottom, which is 2x, all over the bottom squared. I don't need to simplify this. Even if I was asked to like simplify in general, there's no reason to simplify this because I'm not trying to find the derivative simplified. I'm trying to find the slope of the tangent line. So I'm going to say, great, if I plug in 1, then my slope of my tangent line at the point x equal to 1 is going to be 1 squared plus 1 times 2 minus 2 plus 1 times 2 times 1 all over 1 plus 1 squared. So let's say I've got 2 times 2, which is 4, minus 3 times 2, which is 6, all over 2 squared, which is 4. So I've got negative 2 over 4, which I should simplify to negative 1/2. I mean, some amount of simplification is a good idea. And then the rest of this is going to be writing my equation as y minus y1 equals my slope times x minus x1. I would encourage you to write this before you write any equation, just so that the person grading your work knows you knew what you're supposed to do, even if you make a mistake after that. So then we're going to say that, oh, I don't know what my y1 value is. I have to plug in x equals 1 to here to find my y value. So my y of 1 value is going to be 2 times 1 plus 1 over 1 plus 1, which is going to be 3 over 2. So I'm going to get y minus 3 over 2 equals m equals negative 1/2 times x minus 1. And again, I will point out that technically this is correct. This is a perfectly valid answer, and we should not have to simplify it per the instructions. If I was writing this question, I would have phrased it as find the equation of the line in the y equals mx plus b form, so that then you would have to do the work to simplify it. So if we had to simplify it, it'd be y minus 3/2 equal to negative 1/2 x plus 1/2, and then we would add 3/2 to both sides to get y equal to negative 1/2 x, and 1/2 plus 3/2 is 4/2, which is 2. But I definitely take a don't simplify instruction very literally. I wouldn't simplify until I got to the end if I had time at the end. And it's annoying to put the answers in the box here because I would just want to be like that. So you should make sure you write your answers in the box. I don't love, but I get it. Makes it easier. Makes it easier to grade it. All right. We got time still, right? Yep, it's 3:23. We got 7 whole minutes. Calculate the derivative of the given function using standard derivative rules. You do not need to simplify your answers. Okay. So I see a couple things here. I see let's see a very similar function as before. not very original there. Plagiarizing your own work. Okay. So let's see. So we're gonna use the product rule and the chain rule. So I'm thinking of this as one piece, this as another piece. It's totally fine to write. Like you could totally give the pieces of your product names and be like, okay, I know that I need to have G prime times H plus H times G prime. Fine to write those notes on your test to yourself. And then we're gonna be like, great, okay, G prime, so it's gonna be 5 times my stuff to the 4th power times the derivative of my stuff, which is 2x. And then we're going to multiply that by h, which is 2x plus 1 cubed, plus, and then I'm going to have x squared plus 1. I wrote the wrong thing here. That is terrible. I wrote g prime times h plus h times g prime. Ugh, terrible. It should be g prime times h plus g times h prime. Goodness. So x squared plus 1 to the 5th times the derivative of h, which is 3 times 2x plus 1 squared times derivative of 2x plus 1, which is 2. And we definitely do not want to simplify this. So I will say when you're doing this test, if you think you're about to write down your final version of the answer, you probably should write it down in the box. I would want a bigger box though, clearly, because my answer was written in a larger amount of space than the box would have given me, but oh well. Interesting. X squared times sine times cosine. I think this is a triple product rule question. So again, for any version of the product rule, it's always take all your factors. In this case, we had 2. It's always the derivative of one thing times the other thing, plus the other thing times the derivative of the first thing. So each thing's derivative gets to show up once. So for this one, I'm going to have 3 pieces. And I'm going to have each thing's derivative showing up once, multiplied by the not derivatives of the other 2 pieces. So here, if I'm thinking of this, no, I don't even want to write this down. So I'm going to have the derivative of x squared, which is 2x. How am I going to show my work here? Right, because I feel like we can just write the answer, but I feel like that's not showing enough work. So what I would probably encourage you to do, if you know the triple product rule, is to just say, okay, this is going to be f times h times j. Don't use the letter that's already the name of the function. So then my derivative is going to be f prime times h times j plus f times h prime times j plus f times h times j prime. Right? Each derivative shows up once, multiplied by the rest of the not derivatives of the other pieces. So in this case, my f prime is going to be 2x, and then it's going to be times sine times cosine. Plus, then it's going to be x squared times cosine, which is going to be x squared times cosine squared of x. And then it's going to be x squared times sine times negative sine. So it's going to be minus x squared times sine squared of x. I don't like this one. Oh, sorry, you can't see that. Sorry. I don't love this question. I don't feel like it's great for showing work. But it is what we have seen here. If you wanted to show more work, because I feel like this one it's kind of like I feel like I haven't maybe shown enough work here. You could kind of just think of it as x squared times sine x and cosine x. And then if you're taking the derivative of all that, you say, well, it's going to be the derivative of x squared times, leave the other piece alone, sine x times cosine x, plus x squared times the derivative of that piece. And then you can just write the derivative of that piece. And then in the next step, use the product rule for the derivative of that piece. Then it's going to equal 2x times sine x times cosine x plus x squared times sine x times the derivative, or I should say the derivative of sine x first. So cosine x times cosine x plus sine x times negative sine x. That might be a better way to do a problem like this, just so that you're actually displaying the work that is happening. If you just memorize the triple product rule, I kind of feel like you're maybe he's not gonna see that you knew the work to get there. I don't know. Yeah, I don't know about that one. What else is on their plate here? We got 1 minute. Sure, let's do these ones as well. A of t is the, it's like it's kind of small to read there. A of t is the natural log of 2t squared plus 2t to the fourth plus 3t squared. And the derivative is going to be 1 over the stuff times the derivative of the stuff. So in this case, my derivative is going to be 1 over 2t to the fourth plus 3t squared times, in parentheses, the derivative of that stuff, which is 8t cubed plus 6t. End of story. And let's squeeze in the last one on this page. The derivative sine of e to the t squared. Well, that's going to be sine of some stuff. My derivative is going to be cosine of the stuff times the derivative of the stuff. And then the derivative of e to the t squared, well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. I'm kind of showing more steps than I really need to here. And then finally, it's going to be my cosine of e to the t squared times e to the t squared times 2t. I would say if you happen to end up writing your final answer somewhere that's not in a box, put it in a box. They probably can't not give you credit for it, but probably a better idea just to write it in the box. All right, it's 3:30. I should stop. See you on Thursday for class, but not for office hours afterwards because I have a meeting I have to go to.